Hi folks. It seems we're destined not to have that many in-person classes this February, so here we go with another video lesson to polish off transformations of functions. If you didn't watch the video from last Friday that talks about combining the transformations, you might want to go back and take a look at that. That really has the crux of what we're looking at, which would have been sort of this slide here, where they're all combined. That stuff's on the February 11th post on Google Classroom. In terms of the stuff we're doing today, there's PDFs on Google Classroom of the notes, of the filled in notes, of the practice, of the entire Oxford textbook, and of an optional review sheet. So let's dig in here. We've got a function q of x that's been vertically stretched by a factor of 2/3, horizontally stretched by a factor of 1/3, reflected in the y-axis, then translated right 7 and up 2. And just to be clear here, sometimes right 7 and up 2 is shown this way, 7, 2, as a vector. The top number there means right-left transformation, and the bottom number means up-down. So really we're wondering, what's going on with q of x? It could have some number in front that would be its vertical stretch factor. It could have some number in front of x that would tell you something about its horizontal stretch factor and maybe one of its reflections. X could have something added or subtracted from it, and then we could have something tacked on to the end. Okay. Each of these transformations is going to have something to do with one of those parameters. So vertically stretched by a factor of 2/3. That's going to tell us that a is 2/3. And the letter that we use, the a, is not important. It's really that it goes in front of the whole function. Horizontally stretched by a factor of 1/3. Okay, so let's just think about that. If you get a horizontal stretch by a factor of 1/3, that means that your b value must have been 3 to give you a stretch factor of 1/3. Reflected in the y-axis. So to get flipped through the y-axis, go from one side of it to the other, that means that this b value must be negative. And let's check that out from the original sheet of all the transformations. You can see there in red, it says negative b means a y-axis reflection. That's because reflecting through the y-axis changes your x value. Lastly, we've got these translations. So if we want to talk about how it's being moved, right 7, h is 7. But more to the point, we would see x minus 7 in that bracket. Up 2 means that k is 2, or that sends us up 2. So the final equation for the function would be 2/3 q, which is the general shape of this function, we don't ever know what it is, of negative 3 brackets x minus 7 plus 2. That's all those features in one graph, all of those transformations. At this point, it's pretty abstract because we don't really know what the function q is, but it's some function out there. Let's try something that is less abstract. Let's try a particular shape. So in this one, we've got a weird shape graph called f of x, and we're asked to sketch f of negative x plus 1. Let's think about the general form that we like. We like it to be in the form y equals a f of b x minus h, really could be plus or minus h, plus k. You might be tempted to right away go ahead and generate this sketch and talk about all the transformations. So you might be thinking, it's a vertical stretch by a factor of 2. It has a y-axis reflection. And then you might say, well, and it's also moved to the left one, because that x plus 1. The problem is, it's not quite in our preferred form. What we would like to have is the coefficient of x factored out. So that negative in front of the x should really come out here. As you could think of it as a negative 1, brackets x minus 1. You can see now how it looks a little more like that form that's in green. You've got x plus or minus something, but there's no coefficient directly beside the x. And again, you can think of this as -1 if you prefer. I think that's a bit weird because I don't like to think about a stretch factor of 1. Most of this stuff is still the same. It's still a vertical stretch by a factor of 2. It's still a y-axis reflection because what's in front of the x is a negative. But it's actually moving to the right 1 when we get it in that nice form. Some people are going to be able to do this graphically. So I want to go through it graphically just to begin with, and then we'll talk about the map. I'm going to take every single sort of important point to begin with, A, B, C, D, and I'm going to mess with them. I'm going to take this point here, A, and I'm going to make it twice as tall. That's vertical stretch by a factor of 2. I'm going to flip it through the y-axis, and then I'm going to move it to the right 1. There is the location of A prime. It's going to be at 2, 8, as long as I haven't botched anything. Okay, let me get rid of the little dots I made on the way. Going to do the same with B. So it's going to have a vertical stretch by a factor of 2. Now, vertical stretch means that the y's are being multiplied, or in other words, it's twice as tall. Okay. Right now it's got a height of 0, or y value of 0. So this vertical stretch is going to do nothing to this point. It's going to get a y-axis reflection. That'll send it to the other side of the y-axis. So it was on the right, now it'll be on the left. And finally it will move to the right 1. So there would be B prime. I'll get rid of the dots that I made on the way, or the dot singular. And I'll do the rest of the points similarly. So here is C. If I vertically stretch it by a factor of 2, it has a height of -2. Now it'll be -4. Or the y value gets twice as big. I flip it through the y-axis, so it was 4 to the right. Now it'll be 4 to the left. And I move it to the right 1. So its final position should be right here. I'll get rid of the dots I made on the way. And that's going to be my C prime. And if I want, I can show the coordinates of each of those. So that's -3, -4. B prime, or the location that B went to, will be at -2, 0. And lastly, let's do D. So again, vertical stretch on this one's not going to do anything because it has a height or a y value of 0. Y-axis reflection, it was 5 to the right. Now it's going to be 5 to the left to the y-axis, and move it to the right 1. There's D prime. And the coordinates of D prime are -4, 0. I'll get rid of the dots that I made on the way, and now I'm going to connect. I'm going to try and do that well. So I know that from A to B it was kind of a curve type thing. Oops, looks like I erased something. There we go. So from A to B prime would be kind of this curvy type thing. Okay. And then I've got sort of a V. Got straight lines connecting them up. Now, do they look like mirror images of each other? I hope so. Mirror images that are stretched out vertically. But they also have that translation that's moved them 1 to the right. So they're not perfectly mirror images of each other through the y-axis. If you find that straight ahead, just visually, great, go for that method. If you don't like it visually, then we can come up with a mapping rule for this. So the point xy is going to be vertically stretched by a factor of 2. So that's 2 times y. It's got a y-axis reflection. Careful here. If you flip through the y-axis, you're making your x values negative. All we have to do is imagine a point flipped through the y-axis to say, oh yeah, that does change the x values going through the y-axis. Lastly, we've got a movement right 1. So here's what it does to every point. It makes the x negative, then it adds 1. That gives us a y-axis reflection and right 1. For the y's, it multiplies by 2 because that's a vertical stretch by a factor of 2. Now we could take all the points, A, B, C, and D from the original, and see where they go. So A on the original was at -1, 4. B was at 3, 0. C was at 4, negative 2, and D was at 5, 0. Run it through the map. So negative, negative 1 would be 1 plus 1 gives us 2 for our x. And then our y value gets doubled, so we get 2, 8. Haha, that really is this point A prime that we found before. The other one will get negative 3 plus 1, so that's negative 2, 0. Ah, that really is the B prime we found before. The next one, negative 4 plus 1, gives us negative 3, negative 4. That's the point we found here. And 5, 0, not surprisingly, is going to give us negative 4, 0, which is the point we found here. So different method gives us the exact same points. You do what you're comfortable with, but if you're finding it difficult to imagine geometrically, the map can really help. So there's one with a picture. Let's take a look at some specific points. We've got some point A, 5, negative 4 on f of x. We're wondering where it goes on some other graph, or some transformed graph, essentially. Okay, so let me make some decent axes here, and maybe I can sort of imagine what this looks like. I think it may be a bit miserable to do graphically. So 5, negative 4. 1, 2, 3, 4, 5, negative 4. There it is. There's our original point. Let's see what happens to it. In this one we have vertical stretch. I'm going to be lazy in terms of how I write them. So I'll say vertical stretch x3. That 2 in front of the x, that's going to give us horizontal stretch by a factor of a half by the reciprocal. And finally, right 4 and up 5. I don't need to write those as coordinates. I want to write them as instructions. Right 4, up 5. Okay. Or as a vector, you could say translated by the vector 4, 5, which just means 4 to the right, 5 up. Okay, if I were to do this, I can imagine what's going to happen to this point. I'm going to have to make it, first of all, 3 times as tall. So let's have this go away. 3 times as tall is going to send it way down here to 5, negative 12. That takes care of this. Horizontal stretch by a factor of a half, so it's going to be half as wide, so that'll give us 2.5, negative 12. And then right to 4 is going to give us 6.5 for our x value. And up 5 will give us negative 7. If you can imagine all that stuff, or draw it out, then great. Otherwise, what we'll do is make a map. And I think the more rough this gets, the more you want to make a map. So for me, I'd be thinking, I've got all these instructions in words. Vertical stretch by a factor of 3 means y times 3. Horizontal stretch by a factor of a half means a half times x. Right 4 means I add 4 to the x, and up 5 means I add 5 to the y. And now I'm just going to apply that to the point 5, negative 4. Okay, so that would be, if I show all the steps here, this is a half times 5 plus 4, 3 times negative 4 plus 5. So that's 2.5 plus 4 gives us 6.5. Negative 12 plus 5 gives us negative 7. There it is. Now you might think, well, I don't really have as much understanding by doing the map. That's true. You don't get to see it all change, but it might be just as good that you can end up with a correct answer without having to worry about all those fractional points. So let's try the same idea for the next one. Maybe the best plan would be to pause the video and give it a go yourself. And we're back. If you did this one geometrically, congratulations. I'm super impressed. If we did it by map, what would we have? We'd have a vertical stretch by a factor of 2/3. We'd have a horizontal stretch by a factor of, it's always the reciprocal, hey? The horizontal stretches and the horizontal transformations are annoying by a factor of 4/3. And finally, it's gone left 3. And these were both in the nice form where the coefficient of x is already factored out. We can build a map out of that. We'll go to blue and make that map. So vertical stretch by a factor of 2/3 means 2/3 times the y. Horizontal stretch by a factor of 4/3 means 4/3 times the x. And left 3 means -3. That's what it's doing to the coordinates. Looks different in the function, but the map tells you what happens to the coordinates. In particular, we care about the point 5, -4. We're wondering where is its image, which we call A prime. Okay, so again, if I show all the substitution here, that's 4/3 times 5 minus 3 and 2/3 times y, which was -4. You can go off to the side and do all the scrap work for this. I'm going to show all the steps. So this is going to be equal to, that's 5/1 times 4/3. So that's 20/3 minus 3. Okay, right away, 20/3 minus 3, I'm going to need a common denominator. So let me rewrite that minus 3 as minus 9/3. The next one, this is -4/1 times 2/3, so that's -8/3. Or in other words, 11/3 and -8/3. If you want to write exact coordinates for the point as mixed numbers, that would be 3 and 2/3 and -2 and 2/3. We really like the improper fractions, though. What would not be okay would be to call this 3.7 and -2.7. That's not as exact, and it's definitely not 3 sig figs exact anyways. All right, so again, you could do this geometrically, but because of all the messing around with fractions, it's probably not as pleasant. All right, domain and range with transformations. To find the domain and range of a transformed function, simply apply the transformations to the boundaries. So we're going to write the domain and range of y equals f of x, which we have yet to decide on. Let's make it, I don't know, maybe it'll, well, I still got it on eraser, so that doesn't help. Let's make it go from here to here in a little curvy bit. I don't know why I put an arrow on the end. Let's undo that. It rightly assumed that it's smarter than I am, but in this case it didn't read my mind quite right. Okay. And then sort of a linear bit, and let's do, oh, I don't know, maybe another zigzaggy linear bit. Nope. Let's undo that. I don't want it to end at exactly the same spot. Let's change this up. Now, in the filled-in notes, I might have changed, I might have decided on a different function if you're looking at that PDF. But let's go with this one. All right, so if I want to make the graph of -2 f of 4x, let's think about that. That is going to be, first of all, the first thing you see is negative, so that's an x-axis reflection. It's going to be vertical stretch by a factor of 2, and it's going to be horizontal stretch x1/4. Let's write the domain of the original. So the domain goes from -4 all the way to 2. And the range goes from -1 all the way to 3. Now you could have also written these in interval notation, so that's from -4 to 2, and from -1 to 3, including the endpoints. One way that we can generate the domain and range for the transformed function would be to actually make the transformed function. Another way would be just to imagine what happens to each of these points. Let's make the transformed function. It'll be fun. X-axis reflection. So I'm taking this initial point here, I'm flipping it through the x-axis, ends up here, vertical stretch by a factor of 2, so it's twice as tall, and then 1/4 as wide. So it really becomes the point -1, -2. You could probably pause the video here and try and come up with this yourself, or you can follow along, and I'll do the same thing. So x-axis reflection brings it down to -3, twice as tall, -6, and then 1/4 as wide would give it the point -1/4, -6. That's the image of, if we're labeling these A, B, C, and D, this would be A prime, and this would be B prime. Similar kind of stuff going on with C, so it would be flipped through the x-axis, twice as tall, and 1/4 as wide. C prime is going to be at 1/4, 2. And let me get rid of some of the little dots I've made on the way. And lastly, D is going to be flipped through the x-axis. It's on the x-axis, so that does nothing to it. Vertical stretch by a factor of 2. It's got a height of 0, or a y value of 0, so nothing happens to its height or vertical stretch. What does happen, however, is that it gets 1/4 as wide. So it used to have a width of 2. Now it's going to have a width of 1/2. There we go. And we can connect this all up. I'm going to zoom in to try and do it properly. So it's got kind of a curvy bit here, and then a linear bit that's very, very steep between these two, and then a linear bit here. Once I've got that, I mean, finding the domain and range is no big deal. Okay, it's going to be from -1 to 1/2. I can just see the x values. The y values, the range is going to be from -6 all the way up to 2, which I can show as an inequality. What you might notice is that you could have done this probably with less work by taking this x value and timesing it by 1/4, because a horizontal stretch by 1/4. Times 1/4 gives us -1. Okay. The endpoint, which is 2, times 1/4, 1/4 of 2 is 1/2. There we go, with a little less work. The range, you do have to be aware of our reflections. So let's pick a nice color here. If I'm doing an x-axis reflection and a vertical stretch by 2, I'm taking that 3 and I'm timesing it by -2, essentially. I'm taking the y values and timesing them by -2. So 3 times -2 would be -6 at one boundary, and then 2 at the other. -1 times -2. Thing to be aware of is the order of the boundaries can switch when you also have a reflection. So it would be silly for me to say, y is a value in between 2 and -6. It's bigger than 2, but less than -6. I mean, I'll give you $10 if you find me a real number that is bigger than 2, but less than -6. So we did have to change the boundaries. I think that drawing it out saves you from some of those errors, though it can cost you a little bit of time. If you found it difficult to draw it out just graphically, feel free to use the map. And lastly, finding the equation. So 2 graphs are shown. One's labeled f of x. No, it isn't. Not yet. Let's label this one in red to be f of x. Find the equation of the other graph in the form of a transformation of f. When we get these questions that ask us to find the equation given some pictures, a lot of times people will try and just jump right to the answer. I think the better plan is to try and write what transformations are happening in words and then translate that into mathematics. So when I look at these two functions, one thing that jumps out at me is that the blue one is upside down. Maybe I'll do this in blue. Ooh, so it'll be nice and consistent. Upside down. I also might notice that it is taller. Now the first one was 4 units tall. The red one's 4 units tall. The blue one is 8 units tall. So it's twice as tall. Right? Let me write that. Twice as tall. None of this is very mathy yet. I also noticed that it's kind of smushed in. It's half as wide. The red one was 8 units wide. The blue one is a mere 4 units wide. So it's half as wide. It's twice as tall, but it's half as wide. And there's also some sort of translation. But the stretches kind of mess up what the translation or the shift is going to be. So I'm going to leave it at this for now and deal with the translation. Maybe I'll just write translation of something. And typically we want to translate or shift last. Let me write these better in terms of mathematical terminology. Upside down means an x-axis reflection. Twice as tall means a vertical stretch by a factor of 2. Half as wide means horizontal stretch by a factor of a half. At this point, I'd actually do those things to it. I would graph it with all those transformations. So every point is going to be upside down, twice as tall, and half as wide. So this point right here, nothing happens to it vertically. You can't flip it through the x-axis because it's on the x-axis. You can't make it twice as tall because its y value is 0, but you can make it half as wide. Same thing with the other end point. We can make it half as wide. Now this one here, the one at the very top, I can flip that through the x-axis. I can make it twice as tall, so it ends up right here. Let me get rid of some of the little points that I made along the way. And when I do these first 3 transformations, this one, and this one, this is the shape that I get. Now it's easy to see what kind of translation needs to happen to this. Translation of 1 unit right. If I took this purple one and moved it 1 to the right, I'd have the blue one. Let's sketch that all out in mathematics. That means y equals. It's upside down, so x-axis reflection means the first thing you see is a negative. Twice as tall, so that's 2 times the whole function. The y value is twice as big, and it's turned negative. Half as wide. Be careful here. That's horizontal stretch by a factor of a half, which comes from a 2 in front of the x. And then we're going 1 unit to the right, so that's x minus 1. That gives us the correct equation for the blue one. We can check it out on Desmos in a second. But if this is sitting okay with you, then head over to the textbook, the Oxford textbook, that we haven't been using that often. Check out page 140 to 141, numbers 1 to 3. You should spend somewhere between 15 and 30 minutes on these. Don't go anywhere beyond that. And let me know if you have questions. We'll definitely take this stuff up in class if we do have questions. But yeah, good luck with it. So here we are in Desmos. I've graphed f of x. There's its equation. If I were to ask it to graph negative 2 f of brackets 2 brackets x minus 1, it really does give me that graph that we were looking for. It even did it in the right colors. That's so nice. All right, if I can find it, I'll put the Oxford questions up here on the YouTube video as well. Okay, here we are on page 140 of the textbook. It is page something else of the actual PDF. And it was page 151 of the PDF. Here we are on page 141, which is page 152 of the PDF. And you can just pause the video and take a look at these. And here come the solutions. Here we are on page 664 of the text, which is 675 of the PDF. And there are the answers. In number 1, they're actually asking you to graph them, but in the answer key, they just give you the description. And here we are with 2 and 3. All right, folks, good luck with the material. Let me know if you have questions. Take care.